Hi guys, this video is about explaining the code of my PID controlling system. Before we talk about the code, let's see what the code is basically doing. So first we have a platform which we can observe which angle it is at. For example, let's say the platform is a rod and the rod is connected to the motor. And on the motor there's a encoder, which is a device that counts how many rotations the motor has done. And using that encoder I can get the number that tells me how much the motor has rotated and where the motor is at by storing it in a variable. And using this I can do adjustments on the motor to make it go to where I want. And this number is a whole number. So if I wanted to go to so the pulse is 0 at the beginning, and if I wanted to go to 200, then if it's less than 200 it will move, and as it moves it will gradually increase and go to 200. Okay, so let's assume the scenario is when the system begins, everything is perfect and the platform is where it should be at 0. And when I push it, it will be offset and it will perhaps go to -10 or +10. And the P part is the part that looks at how much it is off, and the bigger it is off, the more power the motor will be given to restore to the target position. And then the second part is the D part. Because there's momentum in the system, I don't want my system to be unstable and keep on oscillating. So there's a part of the code that calculates when the motor should stop or decelerate, so that it will stop at the target angle instead of oscillating. And the last part is the I part, which makes the system more accurate. It makes the system more accurate because if you don't have I, there may be some error in your angle, but I makes it so that if it's not at the correct angle, it will adjust it. It does it by adding all the error together, so the longer you are displaced, the bigger I will become, and it will be enough to bring the motor, bring the output to the desired place. Okay, so with that being said, let's look at the actual code. This code is done by a function. This function takes in the target angle and turns the motor to that angle. So to actually bring it to the angle, first we have to calculate at what pulse is the target angle. So there's a relationship between the angle of the system and how many pulses that needs to be pulsed until the angle is reached. This is just the motor gear reduction ratio and the 360 degree per rotation. And I can get the target pulse count from the target angle. Later on we'll use this target pulse count to calculate the change needed. The PID system changes the motor by adding all three parts together in this code, in this line of code. The change on the motor is equal to the P part plus the I part plus the D part. The I part is fairly simple. So it is the position error times a coefficient, which means that the bigger error you have, the bigger output will be given to the motor. This error is calculated by subtracting the pulse count from the target pulse count, which means that if my current pulse count is -10 and my target pulse count is 0, then the position error will be 10, which means that it should move 10 pulses more. It should increase 10 pulses. And then the second part is the integral error. And this is done by this code. Here we add the position error each time to the integral, to this variable. So if I'm not at the target angle, but the error is too small so that the motor doesn't move, so I want it to be more accurate, right? So this part will be bigger and bigger if it is not accurate, and it will be big enough to change the motor position again, and it will become accurate. And this is the integral part. The last part is the D part, derivative times a time coefficient. This part actually isn't a positive number. The function of this derivative is to decrease the change of the motor, which means that if the motor is approaching the target, then this part will make the sum of these smaller so that the motor can decelerate. And this D part is calculated with functions. Functions that have a change in value when the input is approaching to 0, which is, I'm assuming that 0 is my targeted angle. So this is a square root function. As you know, the square root function has a big change when the input is near 0. So using this function and manipulating it, I can get a function that will return a big number if it's approaching to the target. And if it's approaching to the target, this big number will be subtracted from the change, and it will cause the motor to decelerate. And this is how I designed my PID.